The following tutorials will teach you how to test a differential protection relay with the Advanced Differential Test Modules. As an example, we will test a Siemens 7UT613 differential protection relay. In this tutorial, we will cover the test object and the global hardware configuration. You can test a differential protection device with the Differential Test Module or the Advanced Differential Test Modules. Since the Advanced Differential set offers more features, we will use these modules to test the differential protection device. For testing the Siemens differential relay, we will make use of a new OCC test document. The four Advanced Differential Test Modules are diff configuration, diff operating characteristic, diff trip time characteristic, and diff harmonic restraint. We insert these four modules into the OCC document. According to Omicron's Ohm's law, we start with the test object. Fill out the entry fields in the Rio block device first. In our example, the protected object is a transformer. The CT ratio data is not relevant here since it has to be entered into the Rio block differential for all windings. The Rio block differential requires a lot of information, but once you have completed it, the testing of differential protecting becomes easier since all Advanced Differential Test Modules make use of the same Rio block. The differential block contains 5 tabs. The first one is the protected object, the second one the CT. In the third tab, you enter the information about the protection device. In the fourth tab, you draw the characteristic, and in the last tab, you enter the characteristic of the harmonic restraint. We start with the information about the protected object. In our example, the protected object is a 3-winding transformer. In the picture, you see its nominal values. Now enter the nominal values of the windings, including the vector group and the star point grounding. In our example, the vector group is YYND5, so the star point of the secondary winding is grounded. The nominal currents are calculated automatically from the power and the voltage values. In this tab, you enter the data of the current transformer. In the picture, you see the values of the CTs in our example. The star point of the CTs can be grounded towards the protected object or towards line. In our example, all star points are grounded towards the protected object. If at least one winding of the protected object is grounded, you can check the Use Ground Current Measurement Inputs box. Then the residual current will be generated on the configured output. Remember to enter the information about the ground CT nominal values. The Protection Device tab is where you enter the relay settings. Set the formula for the bias current calculation according to the relay manual. If you have no access to the manual, check the Test Universe help to see which bias current formulas are commonly used by the different relay manufacturers. We choose the formula for our Siemens relay with a factor of 1. The maximum test time restricts the time for each shot to protect your relay. The delay time is the time in between consecutive test points. It is used to give the relay time to reset. Next, we have to specify the current settings. Therefore, we have to look how the characteristic is built. Small differential currents are also possible under healthy conditions. They exist due to transformer magnetization, tap changer, leakage, and saturation effects. The addition of all these effects represents the maximum differential current that is possible under healthy conditions. The differential characteristic is an approximation to all these effects. In our example, the characteristic starts at the low set value, which is 0.25 times the nominal current. It rises to 6 times the nominal current, which is the high set value. Above this value, the relay always trips independent of the stabilizing current. Input these two values, low and high set, in the entry fields. Consider the operating time for the particular relay when it comes to specifying the time settings. Check the manual and enter the tolerances for the operating time and the differential current. The output values are calculated based on the reference winding and the reference current. Note that these settings have to match the relay setting. This ensures that the differential and bias current values calculated from the relay are equal to the values visible in Test Universe. If you selected Protected Object Nominal Currents, the currents calculated in the first tab will be used as reference currents. If you select Current Transformer Nominal Current, the CT nominal currents entered in the second tab will be used. Depending on the network configuration, zero sequence elimination can be necessary in case of a single-phase fault. A typical case scenario is when a transformer is isolated in one side and grounded in the other. A fault outside the protected zone can lead to a false trip if no zero sequence elimination is applied. This way, the zero sequence components are subtracted so the currents at both sides are comparable. This operation may either be performed within the relay or by using interposing transformers. You have to specify if the zero sequence elimination is applied so that Test Universe adds the zero sequence component to the output currents if necessary. In other words, Test Universe reverses the relay's operation to ensure a perfect match between the calculated values from the relay and the test point specified in the test module. The Characteristic Definition tab is used to enter the characteristic. Each line segment is defined by its start and end points. Often these points are not given in the parameter set of the relay directly. Then you have to calculate them from the information available. The picture shows the points and slopes which are given in our example. From these values, we have to calculate the intersection of the lines by using the straight line equations. We get the 3 points required to define the characteristic in Test Universe. Check the Auto Init Start Point box to take the endpoint of the current segment as the start point of the next segment. The harmonic restraint characteristic can be defined in the Harmonic tab. You have to specify which harmonic component is subject to test. In this case, the harmonic restraint is activated for the second and fifth harmonic. The second harmonic is part of the inrush current that appears at the switch-on operation of a transformer. Enter the threshold for the harmonic restraint and define the tolerances. We keep the default value of 20% since it matches our relay settings. The fifth harmonic restraint prevents false tripping of the relay in the event of overexcitation. The threshold for this harmonic is set to 45% in our example. Click Update to validate any change in the entry fields. Our characteristics for the harmonic restraint are straight lines. If the characteristic is composed of several segments, you can enter the start and end points of each segment as we did in the Characteristic Definition tab. Now, confirm the dialog to save the information. The next step in Omicron's Ohm's law is the global hardware configuration. Since we are testing a differential protection, we need 6 current outputs, 3 for each winding under test. No voltage outputs are required. Name the outputs accordingly in the Analog Outputs tab. Regarding the binary inputs, only the trip command is required for this test. The Diff Configuration Test module tests the wiring and configuration of the relay by simulating faults that are located outside the protected zone. If in such a test case the relay trips, this indicates a wiring or configuration fault within the protection panel. This video tutorial will focus on the configuration of the test module. Check the previous tutorial to see how the setup of the test object and the global hardware configuration is done. Before going any further, check the local hardware configuration to verify that the current outputs and the trip signal are enabled. The test view provides 4 tabs to parameterize the test. A single-line equivalent circuit diagram for the protected object is shown on the right-hand side. The binary outputs can be activated or deactivated from this tab. The General tab contains the information about the fault and the trigger conditions. For the sake of simplicity, this video tutorial will only show the test with regards to the primary and secondary windings. Remember, if you want to test the tertiary windings, you must add a new test module to the OCC document. The default setting here is Fault Primary Supply Secondary. However, we can locate the fault at the secondary side. The single-line diagram changes accordingly. For transformers with 3 windings, you can apply a load current. This load current is applied to the 3rd winding, as displayed in the single-line diagram. The use of the load current is not required by our relay. This test module gives you the option to check the readings from the relay and assess the results manually. The test time is the maximum period of time that the test current is output. Therefore, select a large enough test time that allows you to enter these values. Check the Apply Voltage box to enable the voltage output of the selected winding if necessary. To test a line differential protection, 2 or more CMC test sets can operate synchronized by a GPS, a PTP, or an iRig-B time reference. Choosing primary, secondary, or tertiary defines the currents to be injected when the CMC test sets are triggered. Choose the trigger condition. In this example, we just use the trip signal. A relay trip is not expected during the execution of this test. If a trip is detected, the Diff Configuration Test module will automatically evaluate the test as failed. If no trip is detected, you have to assess the test manually. In the Test Data tab, choose the fault type and add the test points. The nominal current refers to the selected fault side, which is the secondary side in this example. The single-line diagram shows the resulting currents to be output by the CMC. The Test tab is where you assess the test. Select the values that you will read out from the relay. For example, the differential and the bias currents. Start the test and input the values measured by your relay. Since these values are correct and the relay did not trip, we can assess the test as passed. The actual values read from the relay will be saved in the report for full documentation. The Differential Operating Characteristic module tests the operation of the protection device for faults inside the protected zone. This video tutorial will show you how to configure the test module. Verify that the current outputs and the trip signal are enabled in the local hardware configuration. The test view displays the differential characteristic that you have defined in the test object. The General tab contains the settings of the test and the trigger conditions. First, choose the test method from the drop-down menu. In our example, we test from primary to secondary. You can apply a pre-fault condition for those relays that need to stabilize before the fault inception. There is also the ability to apply a voltage output if required. For end-to-end testing applications, it is possible to use a synchronized trigger. Since we want to test the operating characteristic of the differential protection, we use the general trip command as the trigger. Both shot test and search tests are available in this module. The shot test allows you to place different test points in the operating characteristic diagram. You can quickly confirm whether the operating characteristic is within the specified tolerance band. If you have a look at the characteristic in the diagram, you will notice that it changes depending on the selected fault type. This is called combined characteristic. Now we will see how it works. Let's take the following distribution of currents for a single-phase fault. We can see that the currents of the faulted phase are twice the currents of the non-faulted phases. The bias and differential currents can be calculated out of these values. Now we can locate these points in the diagram. The faulted phase will not lead to a trip. The test point falls within the blocking zone of the characteristic. However, the relay will trip because of the currents in the non-faulty phases. For this reason, the characteristic for the non-faulty phases has to be adapted in order to match the relay's behavior. The characteristics of the faulty and the non-faulty phases are then put together to get the resulting characteristic. The characteristic that you see in the operating characteristic diagram is adapted automatically to show whether you can expect a trip or not. We will now test a three-phase fault as an example. To test the slope of the characteristic, place one shot below and one shot above the start and the end of each segment of the characteristic. Place the shots close to the tolerance borders to check that the characteristic is correct in its limits. Use the available entry fields of bias and differential current to add test points or directly use the diagram for this purpose. Now we are ready to start the test and assess the results. It is possible that some test points turn pink during the execution of the test. This means that the point could not be tested because the test current exceeds either the test range of the connected CMC or the relay limits specified in the test object. To get more information about the icons, search for status icons in the Help section. You can only perform a search test or a shot test in this test module. Copy and paste the diff operating characteristic test module to keep your settings and to perform a search test. Also, only one fault loop can be tested in one module. You will need a separate module for each fault loop. The search test allows you to find the exact position of the operating characteristic. To insert a test line, enter the value for the bias current or right-click in the diagram. You can choose whether the nominal characteristic shall be ignored in the search test. If you check this box, the test module will search the characteristic of your relay along the test lines. If you do not check the box, the test module will only search the characteristic inside the tolerance borders. The resolution determines the accuracy of the search test. The test module will take the larger of the absolute and relative values for each test line. We can keep the default values for the resolution and start the test. As we can see, the search lines have been assessed as passed. As expected, the exact position of the characteristic is within the tolerance band. In this tutorial, we will introduce two test modules, diff trip time characteristic and diff harmonic restraint. The diff trip time characteristic test module checks the trip time of the protection device. The diff harmonic restraint module tests the behavior of the differential protection for the harmonic restraint. Starting with the diff trip characteristic, verify that the current outputs and the trip signal are enabled in the local hardware configuration. The test view provides 4 tabs to parameterize the test. The binary outputs can be activated or deactivated from this tab. In this test module, you can use different tolerance values than those you specified in the Rio block differential. If you want to enter new tolerance values, check the Use Evaluations Factors box and fill out the entry fields below. Select Apply to enable the voltage output of the selected winding. In the General tab, you can define a pre-fault state and choose the trigger condition. In the Other Settings section, you can choose the windings to be tested. Keep in mind that the fault side is always assigned to the reference winding defined in the Rio block differential. Furthermore, you can set the test line slope, which represents the relationship between the differential and bias currents. Based on this value, Test Universe calculates the bias current for the test. In the operating characteristic diagram, the test line is displayed. Make sure that this line is above the line of the characteristic. This ensures that the trip time can be assessed. Usually, it is not necessary to change the default setting for the test line slope. In the Test tab, you place the shots to test the trip time. We will test a 3-phase fault as an example. The time tolerances are indicated by the red dashed lines in the trip time test plane. To define the test points, you can either enter the differential current in the entry field or right-click on the diagram to add a test point. If you want to add a series of points, use the Add Sweep option. In this case, you must define the start and end values. Enter the step size and add the points to the table. When the test is executed, the test module displays the trip times and evaluates them. We see that the relay trips faster if the test point is above the high set value. In this area, the relay trips independent of the bias current. Now it is time to open the diff harmonic restraint test module. Again, verify that the current outputs and the trip signal are enabled in the local hardware configuration. In a similar way to the other test modules, the General tab allows you to apply a post-fault, a voltage output, and change the trigger condition. In the diff harmonic restraint test module, you can perform a search test or a shot test. It is not possible to run both in the same test module, so we will show you the shot test first. This test makes an estimation of the blocking and non-blocking zones of the harmonic restraint function. We will do the shot test for the second harmonic. Usually, you can keep the default phase shift angle between the harmonic current and the differential current. If you want to use another value, enter it in the entry field. Enter the differential current and the harmonic ratio to add a test point or use the diagram. Place a shot next to the tolerances of the characteristic right at the beginning and the end of the line. In that way, you can test the slope of the harmonic restraint characteristic. Start the test to assess the test points. You can see the results for each test point. To perform a search test, we insert a new module in the OCC file. The search test allows you to find the exact position of the harmonic restraint characteristic. We perform the search test for the harmonic restraint characteristic of the fifth harmonic. To insert a test line, enter the value for the differential current or right-click into the diagram. You can also choose whether the nominal characteristic shall be ignored for the search test. If you check this box, the test module will search the characteristic of your relay along the test lines. If you do not check the box, the test module will only search the characteristic inside the tolerance borders. As expected, the exact position of the characteristic is within the tolerance band. Therefore, the search lines have been assessed as passed.